Welcome to a new test and teardown video. This time it's my new HP AD7528 GSM radio test set. So this one is a signal generator, modulator, GSM base station, call and receive, and a spectrum analyzer, oscilloscope, audio generator, modulation, this and that. I mean, this can do everything you can imagine, but only up to 1 gigahertz, of course. At the front, if we only see the front, it doesn't really look that big, but it is a full mega deep unit, and they say caution 2-person lift. And it's because it's 31 kilos, so it's quite heavy. And yes, it's 61 centimeters deep, so there's not a lot of table left here. And yeah, I left a little bit for connectors and power and all that here at the back. I was told and promised this unit should work, so I will just power it up immediately. And let's go straight to it. And mains applied, and it used about 50 watt. This is 22 watts of idle, and I believe that is oven warm up. So it is at the moment doing oven warm up and stable for that. So we could power. It's 250 watts. Oi, 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 oi. So it's using 250 watts, and of course it powers up. And it should say happy. Yes, exactly. So this is the welcome screen. And it's from 1990. Oops, so we did. What is that? Requires option da 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 da. What the heck is this? So there's some sort of a power cycle. I think we should just. We'll see what happens. Yeah, exactly. You could just skip it. And then I should be able to access the spectrum analyzer modes. That is actually what I wanted to do. We will find plenty of videos online about how to use this as a GSM test, as a call and receive, and all these kind of things. So I don't want to bore you with any of that. My idea for this video was actually to do a teardown video about its internal designs. So that was, my goal, to be honest. Let's just quickly see that it seems to be working. I just went into the spectrum analyzer, and whoa, this is a blinkety slow speed, huh? Let's just test a little bit of its main features. Of course, the spectrum analyzer is really nice and fine. So here I just set it up for 100 megahertz, and I gave it a really weak signal. And yeah, okay, it's not super fast and all that, but definitely it's still usable. You can select the different inputs here, and it says you can't connect a transmitter to this one, but better use the other one. And it says how many milliwatts you can okay, yeah. Just wanted to show the scope. Of course, it's an LF oscilloscope. I'm using the scope input here. You can use audio inputs, and you can use spectrum demodulator and everything like that as the input source to your oscilloscope here. And you can, of course, dial the time base like that, and then it will show you what's going on. I just connected this input here to a signal generator over there, but you can, of course, use its own signal generator. Let's look at the back. So this big hefty casted aluminium frame. Maybe that is one of the reasons for it to be really really heavy. It says 450 watts. It's only using 250. And we got a little bit of connectivity here. 10 megahertz output and a, what's that, 13 megahertz output. That's weird. Reference, scope, AM, and video. So probably this screen is a video. I think, no. This video output is, of course, the demodulated signal from the spectrum analyzer. This is often called a video signal, but it has to be that because that'll be weird. Diagnose. Yeah, okay. Let's see if we can figure out how to open it. Should be fairly easy. Just screwdriver in here, and this is a classic problem with this type of mains connector. There's supposed to be a little plastic thing that goes click, click, and that never ever works. Well, that was easy. I just took the lid off, but look at all that fantastic hardware. Thick aluminum plates. Everything is screwed together. Like tons of screws all over the place, and hold this and hold that, and all the plug-in modules here, and that will be the tiny little screen. I mean, is the screen really not that deep? How cute is that? I'll try and unscrew everything here, and then let's have a look if we can get in there. There's another little funny thing here. It says use 4mm hardware, so that means it's metric screws. What is that? They got tired of all those inchy screws. How cool. So I am inside, definitely. It was quite easy to lift up the different cover plates and all that. And look at that big, massive transformer. So the whole power supply, I believe that is a linear power supply. And they made it real nice with all the transistors here in this cast aluminium frame and a big hefty fan around it like that, and all the capacitors, they are nicely cooled by the fan. Pretty good design. See a lot of transistors down there, fuses and all the goodies. There is unfortunately a very bad smell in here, like something is badly broken, so I need to find that. So when you lift up those modules here, the little end clips, they kind of fall apart like this. So I need to carefully inspect how that is done. And then we got funny loose plates in between them as well. Why is that a thing? This is a little bit odd, isn't it? Oh, so we got some double-sided sticky that is not sticky anymore. Okay, well, weird. Is that supposed to be sitting? No. Well, I hope you can't plug these in wrong. So I need to understand the system here. There's some sort of a numbering system, or I need to mark these somehow. I'll take out 2 or 3 of them and then figure out how to do this. So I figured out the system about all those plug-in modules here. I believe most of them, they're like option modules. And see the text down here, the little white text down there, which is step SA, that means spectrum analyzer, receiver, and so on, right? And that is, of course, the same name written on the module. So that is how it's done. But there isn't anything preventing you to plug it in wrong. It's exactly the same connectors and layout. So that is a little bit weird. I figured out this little detail here. And the other module here had this plate mounted. And it's just some double-sided sticky that makes this a little bit heavier. Or probably this is made of anti-magnetic interference metal called mu metal. And so there's something in here magnetic sensitive, and then they added this extra shield on both sides on that one. Step loop. So here is the bottom of the unit. We got a really nice shield behind all the plug-in modules and RF input connectors. We also got a nice shielded box for all that kind of stuff. And that will be the big motherboard for all the other plug-in modules. Nicely shielded again. Look at all the mechanical details about shielding and grounding and all that. Super nice. What do you think about this? Nasty, sticky slimo. So they added those sticky rubber feet to create a nice, stable support for the power supply board. We got hefty, heavy capacitors, and of course for anti-vibration, of course, you know, you want this to be coupled quite good to the back chassis or the bottom chassis part, right? But they melt, and this is slimy, stinky, and sticky, and really, really bad. So now I need to go and figure out what kind of method to clean this away, and it's so terrible. I'm still fighting a little bit with all this nasty stinky slime, trying to get this power supply out. There are like a million screws from all sorts of directions and little metal plates and whatnot, and all sorts of hidden connectors down here we need to pull, and all these connectors as well. But I think I am soon to have this power supply out, and then I can continue here. But there's one more little detail I want to show you about this backside of this huge motherboard. So all those solderings you see here, that's all the metal shields between all the signal connectors for all the different plug-in modules. Really, really nicely designed. So in here I was able to remove the top shield finally and get access to the rest of the circuit boards. I will of course pull them up in a minute, but what I find here is a little bit worrying. What is going on here? I see some SMA connectors and they have been cut. What the heck is going on? Where are they supposed to go? I mean, that is not okay. Not exactly what I expected. I'm still trying to get the power supply away to clean this completely up and take out all the caps and do all the fantastic things about that. But I will also take away the entire front panel. And then we'll see what's going on down here. Maybe I'll figure out where those coax cables they're supposed to go. Well. This is probably the most complicated linear power supply you will see this entire week. Look at the size of this thing. It is just amazing. It's full of all sorts of fancy, schmancy things. That will be an LM317 in TO3 size. And we got another one over here, biggie size variable power supplies. Rectifiers with heat sinks and all that good stuff. We got some more rectifier diodes. That will be the connector for the transformer. And look at that super beautiful shielded transformer. Shielded cable for all the primary windings. And here is a reefer capacitor. And it isn't even cracked. What the heck? A beautiful, fully intact reefer capacitor. I mean, that will be 1 in a million to see that happen. And of course, a big, powerful fan. About this power supply once again. This is the one that was super nasty. The back side here is just really, really bad. I will of course have to clean all this up and make it nice and shiny again. It is a 4-layer circuit board design, and all of what you see here is a through-hole design. However, what they did to make this all through hole design, a few parts needed for whatever reason to be SMD. So there's a little add-on circuit board here with the SMD parts. Isn't that just weird? Why would you do this? But that is how it is. And also, I want you to see the detail here. This is, of course, a big, powerful fan. And we got access here to the cooling aluminium. On each of the sides here, we got the heat sinks for the linear transistor regulators. We got the connectors right here, and they plug in the connectors right there. Okay, so this all sandwiched up like that. Something here went terribly wrong. Complete overload and meltdown on this regulator right here. Everything is individually fused, so that's quite beautiful. And it looks like those three adds up to one supply rail for whatever reason. It looks a little bit like different resistor values, and they have been way too warm. And look at this thin aluminium part, and it connects to the heatsink in the end like that. It's not a super good thermal connection, right? And then you got the thermal here and all this big frame here and all that. So it's probably not that bad for the power. And there's of course another one over here. It's a little bit similar. Look at this design here. So that will be the emitter resistor is done in copper layout for that one. And it's exactly the same for the other two. It's just, well, let me see if I can show this. I don't know if you can see it, but it is also done in the layout for the other ones. Just in the other layers. Very, very different from what you normally would see. And the power supply is made in USA. And I have seen many of the other boards where it says made in UK. That is also a little bit interesting. So I will have to clean all this up and fix all this. But it's like the most complicated power supply. It's just so full of parts. Have you ever seen anything like this? Look at all those op amps and this is wild. And all the capacitors here, different types, all of them. This is just one hefty power supply. And here in this corner here, we had all the BNC connectors and the IEEE interface. And this layout here is a, I think it's a 6-layer circuit board, 6-layer design. And we even find a little, look at that, tiny little bug. Mechanical design bug. See this capacitor here? Oops, didn't have room for that one. And they also put the component a little bit too close to the connector. Also that resistor there. Yeah, well. 6-layer board for that one. I will, of course, go through all the different circuit boards and show them. So we will get a nice overview of all the different parts. There's another, at the side of this unit, we have this, so this is a mixer. This is the one that's, I think this is the one that handles the 500 to 1000 megahertz range. So we got the IF, LO, and RF. So this is the, the frequency expander or something like that. It handles the, to make it double the frequency. And we got a little filter and a mixer. So this is how it works. A little bit of diodes, and it looks like a little bit like that. But there's only a 5-volt supply for this one. So I'm not super sure about this part here, but it's, of course, I know exactly how to put this back anyway, so no worries about that. So here's the front panel with the CRT, and I carefully pulled out all my connectors here so I can put them through the little holes and all that. So that will be the keyboard and the rotary encoder, volume knob, and the little speaker in one little cable like that. And here is a dummy load. So that will be, I mean, why is this cut like this? I still haven't figured that out. It seems like this unit has been replaced from another unit, and for whatever reason, I mean, why would you have a heat sink like that and a dummy load or feed through terminator attenuator, right? And it goes where? There's no way. This don't make any sense. But of course, we'll have to look into the RF section underneath the CRT. Before I pull out the entire CRT system, I also want you to see this little detail here. So around the CRT, this is the screen, but you can see here, there is a metal film with a thin, I don't know if this is super easy to see, but there's an electrical shield that is, yeah, you know, you can see through the metal. Here you go. I went to my super macro. Now we can see this little metal film here, right? Here's the front end, the inputs. We got some, I believe those will be Teardown relays. They're super famous for being ultra fast and super good. Yes, they read Teardown, as you can see right there. And we got the two BNC connectors, relays and coax cables that goes to the mixer here. We got also, I believe we got some mixers and filters and stuff like that here. Amplifiers and attenuators and all the different little pieces here in nicely. I mean, look, it's inside all these nice metal shielded rooms. Just fantastic, the design here. And this is, of course, a very, very heavy unit. Maybe we can also look at the other side. I don't think that is super easy, but because I don't want to break and destroy this. And when you pull out the screws here, see, it's real easy to cause damage to things. So you need to be really, really careful what the heck you're doing here, and only open and close one little part at a time. But I think I'll be able to show the other side as well. But let's look and see if I can do that. The other side of the unit contains all the control logic. We've got some serial interfaceable parts. We see those parts here all over the place. And I believe that will be the I/O chips they use to control every little bits and bytes all over the place. Tons of DC filters, local capacitors, a little bit of op amps and filters. Super good filtering on every little thing. I mean, look, there's half of this board that's filtering and handling before it goes to the connectors. Also, we see a little bit of amplifiers and stuff here that has not been mounted for whatever reason. Maybe they're using the same board for other frequency range units as well. And that will be another interface. See again, all the filter components. Fantastic. So I'm happy I was able to get all the way into the CRT, because look at how dirty the screen is here on the front. But there's another thing that bothers me a little bit. Can you see how burned in the CRT is? It's completely destroyed. Oh no, menu. And I actually did see this when I went through the different menus. I could see the darkened phosphor. Oh man, it's really bad. That's a little bit sad. And here is the absolutely beautiful CRT unit. And I was able to clean the screen real nice and beautiful. But I don't know if you can even read the menu that is burned in here. But anyway, OmniVision Incorporated, Glendale Heights, Illinois, right? And it's the CRT is from Taiwan. Got a little focus knob right there, and a Hewlett Packard part number. Of course, this is made and manufactured for HP for all their different spectrum analyzers and whatever. So, but I'm quite happy this one works and all that, but it's really burnt in. I will just super duper clean it and it's gonna be fantastic. Beside the burn in, obviously. It was nice and sharp, the picture. I was okay with that. Got some real funny looking. So this is some sort of a varnish around this IC solder point here. That's not super beautiful. And of course, the classic high voltage transformer and a little bit of trimmers here for the deflection and how much of this and that. Some hold, center, brightness, blah 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 blah. All the classic. So now I'm going through all the different circuit boards in this unit. It's probably going to be a very long section of this video, so you can of course scroll real fast to that board of interest. This one is called DAC. This is the DAC board, and it modulates directly into RF. As you see those wide tracks here, that will be RF tracks that goes via amplifiers and filters to the mixer. And there's another RF path this way that goes over here and into the filter sections right there. So it's a little bit interesting. They're using a very fast digital to analog converter, and they modulate directly into that mixer. And out comes, of course, a modulated carrier with that analog signal. So that's I find that super cool, the way that they're doing this. This board here is called Pulse Driver, and it looks really boring from this angle here. What we see it's doing, we got some op amps and timing, and yes, I think this one can do some pulse on off keying and pulse modulation, so we can set up some different rise time, fall times and pulses like that, and that is more or less all this board can do. Not a lot to say about that one. I think this is probably the most boring board of them all. This one is called the receiver, and it's full of all the fancy schmancy stuff. We see this chip here on many of the different boards. I believe this is an I/O expander chip for communication to handle all the low speed stuff on a board like this. And here is an LM1965, and this is an FM IF chip. Got a little mixer here. This is just AM FM receiver and low level stuff like that. This one here is called Spectrum Analyzer, and again we got the little interface chip. We got an AD7525 DAC with the quad output. Got an HP custom chip, probably for some interface and whatnot. We got two AD640. Those two, they're actually 50 dB log amp each, and this explains, of course, the demodulated signal. They take the RF signal and amplify 50 dB each, and then you can, of course, AD convert all this, and then you have your detection range. What you can also see is we got the 11.26 megahertz. We got 3 of them. So that's, of course, filters for the IF. But this one can run with 2 different IFs. It can also run on a much lower and much narrower bandwidth, and that's, of course, done this way. So you select if you want the wide or you want the narrow bandwidth. And here's a little mixer to go down into all the low speed stuff. So that will be the spectrum analyzer plugin. Here is the master clock reference. It is, of course, running at 10 megahertz oven oscillator. And we got 2 little I think this is a PLL. And the other one here is a counter. So you can set up all sorts of frequencies you want. We also got some amplifiers for all your outputs. A nice little shielded box. And again, the little interface chip to control all the different master frequencies. So for the different oscillators, this unit is, of course, using 2 different oscillators, and then they're mixing those 2 oscillators together to a master transmit and receive frequency system. And this is why we have, of course, 2 of these step loop boards, and they are, as you can see here, completely identical. So in this board here, we see this little mixer system right there, and since those diodes, they of course are very temperature dependent, and their performance and behavior is very important for leveling. Here we got a little LM35 temperature sensor with a very high precision and all that. And I believe they measure the temperature in here and compensates and handle all that. What we can also see what they're doing here is we have a little amplifier right here. This is a little field effect transistor. The fun thing is that they only solder one of the 2 ground pins. If you look a little bit careful, can you see the ground pin here? It's not soldered, only the top one. And it's probably because they had the idea they were using or going to use another type of FET. And then they just amplify this way. There's a little track this way. Here is a little resistive power divider. And then you go this way here and here and here. And then we have tons of output. And then the other signal goes, I believe, this way here and out that connector. And of course, there is a 3rd unit looking exactly like this. And this one is called the sum loop. So this one is used to control the other 2 VCO systems into the master output. And this is also why you see your master mixer right here for that. So that is how it's done. Some other modules like this one. I think this is just some low level stuff. You got some filters and some analog switches, relays and such. We also got quite a lot of analog low audio range kind of stuff, and that is done on simple audio range boards like this. There's another board that looks a little bit like this. See? And this one, I believe, is the analog sine wave audio generator. And it can do a few different tones at the same time. And yeah, and here is another one, again, with 8-bit DA converters and a lot of different interface chips to handle that. And again, this is just controlling low speed analog stuff in the unit. It's just so much full of circuit boards doing a lot of things. This one is called RF output, and it's again, there's a little mixer, and we got a lot of little amplifiers and diode switches, filters. We got different signal path that is merged into the output down here. Then there's, I believe this is another output, and it's coming from this way, and it goes also out here. Look at that, some high power transistors. And the reason why you can see the signal goes this way here is if we flip the board, look at that. There is of course a proper ground plane along the signal. So this is an easy way to see signal path for a RF. And most of these boards, they have a layer identification. I don't know if you can see this, but they soldered this one. You can see the number 4 here. If you look at the other side, you'll see 1, 2, and then so this is of course a 4-layer board. They're using 4 and 6 layer boards throughout this unit. Let's look at some of the more juicy boards, right? So this one I called DSP1, and that is of course because there is a TMS43010 C25. So it's a 16-bit DSP. We got, of course, an EEPROM, 16-bit EEPROM. So that is why it's so big and nice. We got some AD converters and analog multiplexer. And here is again a bi-directional first in, first out for communication to external devices. Some boards are really nice and small. This one is probably the graphic card or the graphic output board. There's a little output chip here that is doing this. This is a TMS43010. So this is a graphic processor unit or special optimized CPU for graphics, moving graphics and such, and a little bit of RAM to store the picture. We also got a lot of slow-mo boards like this one. The fun thing is there's a custom HP chip, and then the rest is just super slow-mo stuff. A little RAM to communicate with that one. Analog reference, voltage reference, super duper stable AD588. And here is another AD converter. So I believe this is the general purpose ADC card, because all those many chips we see all over the place here and again up here, that will be analog multiplexers, so it can measure all the different voltages and currents and temperatures on all the different boards. And this is of course used for calibration and live compensations and such. We got a few more of these controller boards here. I believe this one is a custom FPGA or something in that ball game, and it is as you can see here on the type number, HPFC1FS5 and then 0001. And if you Google this, you can of course see this one is used in other HP instruments as well. And here is again this little interface chip, and I believe this one is the clock. Got a decoupling capacitor, impedance matching resistor, and then it goes to clock driver chips. And then there's actually also another crystal here doing some other things. So maybe it needs two clocks. And this is a very normal 27C1024, a 16-bit EEPROM. And look at that. Here we got data buffers. Funny enough, they got two of them, and I think it's just because some timing issues, so they want two of them. But the fun thing is that here you got the 8 low, and we only got 4. How about that? And I've double checking here, it is soldered to ground, so that means we got 12 bits of data coming out of the EEPROM. So this one is a 12-bit device, and that's just, well, it's just super fascinating, isn't it? On the board here it says 8922, and that is of course the unit we are playing with at the moment. And there's another board very, very similar. It got the same, exactly the same custom chip with exactly the same label on it. And here we got DA converters called AD565, and they are 12 bits. And I believe this generates the GSM modulation system, and that is of course why you want a programmable gate array like this to bit bang out everything so it's perfect phase correct, because this is very, very timing demanding. On this board we got 4 crystals. Look at that. And we got a few other really, really weird things on this board. So we got 12.6 megahertz, we got 3.6 megahertz. You can't really see how much this is. There's a, look at that, MT6865. I believe this is a DTMF chip, right? And here we got AM9513. I can't remember exactly what that is. But here we go. This one is an ADC31. So there's another microcontroller, RAM and EEPROM for the software here. And I believe this one is setting up whatever goes on here in the modulation system, right? And we got some output amplifiers. Fascinating stuff. And this, here it is, 8920. And this is exactly the same for the 8920 spectrum analyzer as well. I still haven't figured out why we have this big hole in this board, because there isn't anything there. So why? That's a little bit weird. So we got more CPUs and more FPGAs. I think this is, I call this the FPGA 3. We got again the bi-FIFO, bidirectional FIFO. And here's a Xilinx XC3042 FPGA. And what do you know? A Motorola 68HC000. So this is a 16-bit CPU, 24 megahertz. And that's of course the 16-bit EEPROM with the software for that one. We got 16 bits of RAM over here. And here is, I think this is the last FPGA board. I call this FPGA 4. And here we got 2 Xilinx XC3090 FPGAs. We got a little bit of DAC, yeah, PALs for all the timing and stuff. We got a little bit of RAM. So yeah, definitely heavy duty timing demanding solutions. I mean, this is why you would use FPGAs. And yeah, this board here is a 6-layer board. One of the few 6-layer boards in this unit. Most are 4. Here is another one of the CPU boards. I call this CPU 1 because I believe this is our main software. This is where our main application is running. And there are several things that makes me believe that, but we can see what we got here. We got, of course, another 68 series of CPUs, but this one is the 020. And we got a coprocessor, floating point coprocessor. We got flash, and we got a lot of RAM, but it also got a lot of flash for user upgrades. And what is the 040? That will be timer. And yeah, tons of decoupling capacitors on the back. And nice with all the filters near connectors like that. So this one here I called CPU 2, and this is doing the more demanding stuff. And again, bidirectional 5.0. And here is a full-blown 6820 CPU. And what else have we got here? UART, I/O chips, tons of RAM, and that will be the software in one-time programmable EEPROMs. And this one is running at, yeah, there's a 50 megahertz crystal, and it's divided by 2, and yeah, this is of course designed for 25 megahertz. Yeah, it just keeps coming. I mean, when will this stop? This is another board with DSPs. I call this DSP2. And here we got 2. And they are called DSP56002. So that will be 24 bits of DSP. Super brainy floating point calculations done in insane speed. And you're probably gonna think about what's going on with the RAM here. Look at that, we got 3 chips right there, and we got 6 chips near the other one. And there's a reason for this. So that the RAM modules here, that will be 8 bits. So you need 8 1624 bits. This one is just double, using the double amount. So it's still 24 bits, but just double, right? And they don't run the same frequency. This is also a little bit funny. Why is it so? One is running 20.48 and the other one is running 27 megahertz. That puzzles me a little bit. And this is only a 4-layer board. I am a little bit impressed about that. And I believe the last of the boards, this one I called memory and battery. So all this RAM you see here, that will be battery backed up settings and calibrations and all that kind of stuff. I don't know exactly why we have 2 batteries. This is just because it's a better physical solution. This is also the memory card, and those chips around here, that will be drivers and isolation for that one. I don't know exactly why we have a crystal here as well, and some pals and stuff like that. Why is that? Why is we need a crystal here? But anyway, that was a walkthrough of all the circuit boards in this unit. So now you have seen the full super crazy teardown of this unit, and I will say thank you very much for watching. I hope to see you soon again. Bye bye.